Hi, I'm Krishnakant Singh and I will present our paper S2-Flow, Joint Semantic and Style Editing of Facial Images. This is a joint work with Simone Schaub-Meyer and Stefan Roth. I hope you enjoy the talk. Before going into details, I would like to highlight the main takeaway of our work, which is that normalizing flows coupled with transformation-based consistencies help with disentangling the latent space of a pre-trained GAN, which allows for controlled disentangled editing in both semantic and style domains. As seen, given an input image and an edited semantic mask, we can generate an output image that is consistent with the edited semantic mask. For example, here adding smile. Our method's generated image also preserves the identity of the input image. Our model can also apply fine-grained style edits like changing hair color, for example from blonde to brown, as shown by the example on the right. To the best of our knowledge, our model is the first to enable fine-grained semantic and style edits in the same framework. Editing with generative models has shown great success in recent times. Methods like style space, style flow, etc. have shown excellent editing capabilities by utilizing the latent space of GAN-based models. We show a few examples here. A major chunk of editing methods in the last few years can be thought of as building editing engines that learn random walks in the latent space of GANs. This scheme is attractive because it is a very lightweight solution requiring no or little training. These methods can broadly be divided into unconditional and conditional methods. Next, we go over conditional based methods in detail. Conditional models learn a random walk given a conditional signal. These conditional signals can be attributes, or semantic mask, or text. We now give a brief overview of using S2-Flow compared to these methods. Attribute-based methods provide control editing when the control signals are categorical like hair color or binary like gender. Still, these methods do not work well when attribute values are continuous, for example when changing smile and hairstyle. As the example shows, the user may want a different type of glasses, say small rounded spectacles. Instead, the attribute-based method outputs oversized sunglasses, leaving the user without further control. The issue is fixed in our model by making such edits directly on semantic masks. Semantic methods, on the other hand, provide fine-grained control over semantic edits like changing hair, glasses, etc., but severely lack when it comes to style editing. They typically require a target image when applying style edits as shown. Erroneous attributes like skin color, lip color, and background are also transferred to the output when the user only aims to change the age. Our model overcomes this issue by making style edits in the style space of our model, which provides more realistic looking results and preserves the identity better. Let us compare the editing capabilities of all these models. Unconditional models lack user interactivity and hence provide limited semantic and style editing. Text-based models require detailed text in order to perform control edits, rendering them not user-friendly. Attribute-based methods are not suitable for semantic edits, while semantic-based methods fall short when applying style edits. Our method combines ideas from semantic and attribute editing methods for enabling fine-grained edits in both semantic and style domains. Next, we go over the key idea and component of our model. If we assume an image is made up of two random variables, style code and semantic code, then the image generation process can be described as sampling from the joint distribution of style and semantic codes. Thus, given an image and its semantic code, we can uniquely identify its style code. We then need to disentangle this joint distribution to enable control edits in semantic and style domains. We can marginalize over all possible semantics of the image to get the marginal probability distribution of this style code in the style space. If we repeat this process for many images, then we can learn the style distribution, as seen by the style curve here. One of the first questions is how to model the image distribution. For this, we use a pre-trained StyleGAN's latent space as a proxy for the image distribution. StyleGAN's latent space can generate a diverse set of images that vary in pose, gender, race, age, etc., making it a strong proxy for the actual image distribution. We now discuss the need for disentangling the joint image space. Disentanglement of joint space into its corresponding components help us make semantic and style edits in their respective spaces. This helps in making edits that are disentangled. Now that we know that disentanglement is needed, how do we actually disentangle the semantics and style? For this, we use a conditional normalizing flow model. A normalizing flow model converts a simple known distribution on left into a complex one using a series of transformation functions f using the change of variables formula. This is called the forward flow. The backward flow uses the inverse of the transformation function f for converting the complex distribution on the right to a simple one. A key property of normalizing flow models is that these transformations do not lead to a loss of information. In our model, we use normalizing flows to convert the conditional property distribution of image given semantics to a simple distribution. If this is done over all the possible semantics, we can disentangle the style and semantics of the image. We now go over our model in detail. Given a latent code W, which is randomly sampled from StyleGAN's latent space, it is first fed to the StyleGAN generator G and subsequently provided to the segmenter S and embedder modules E, resulting in the semantic code WSM. We use a frozen deep lab module as the segmenter module, and the embedder's role is to embed the semantics into a latent vector WSM. The input code W along with WSM is fed to a normalizing flow model, resulting in the style latent code WSTY. During the forward pass, the network learns to maximize the conditional log likelihood of image given their semantics. During the backward flow, first the user edits the semantic mask, which results in the edited semantic code W hat SM. The style code obtained from the forward flow along with the edited semantic code is fed to a normalizing flow model which outputs an edited latent code W hat. This W hat is then fed to the generator model to generate the image and its corresponding semantic mask using the segmenter module. During training, we use two transformation consistency objectives: semantic consistency, which ensures that edits made in the semantic domain are reflected in the semantics of the generated image; style consistency, which ensures that the style of the generated image deviates only minimally from the original image. In summary, during training, we first use the latent code W along with its semantic mask to obtain the style code WSTY using the forward flow, as shown here by the blue colored arrows. We then use WSTY and the edited semantic mask as input to the backward flow of our model to obtain the edited image, as shown by the blue colored arrows. Next, we show semantic editing results. Semantic edits can be applied by first performing a forward pass with the input latent code W and using the edited semantic mask during the backward flow, obtaining the edited latent code W hat. We can also edit a real image with an additional step of first inverting the real image using an inverter method like encoder for editing. Our model can perform a wide variety of semantic edits like changing gaze, face frontalization as shown in rows 1 and 2. Our model output images have a high realism and also preserve the identity. Even in the extreme case of randomly swapping the semantic mask, the model outputs an image that preserves the identity and is consistent with the edited semantic mask. We now show results for style editing. For style editing, we first obtain the style code of the image by using the forward flow of our model. We then linearly interpolate in the style space of our model towards the target style attribute WTarget. The target style attribute is obtained by averaging the style codes of all the positive samples for the target style attribute. Here we show the interpolation from left to right of the input towards the target attribute. Our model can apply fine edits like hair color change in the first row and broad edits like age transformation as seen in the bottom row. We now show results for joint semantic and style editing. To do this, we first interpolate in the style space of our model for style editing and use an edited mask during the backward flow for semantic editing. We show results for both semantic editing alone and joint semantic and style editing. Row 1 shows results for adding a smile and changing hair color, while row 2 shows results for adding glasses and changing hair color. As seen, our model preserves their identity while making realistic looking edits. In this experiment, we want to show that S2-Flow can separate the semantics and style. For this, we first fix the style code and we use different semantic masks. Our model generates images that differ in semantics, here the smile, but have the same style. We now fix the semantic code and sample different style codes from the style space of our model. As seen, our model generates images that are diverse in style like age, hair color, etc., but are consistent with the input semantic mask. We now show results for qualitative comparison for the task of semantic editing. As can be seen in columns 3, 4, and 6, our model results are more realistic and preserve the input's identity better than semantic-based methods like spade and mask can. We also show results for style flow in column 5 and attribute-based method. The results show that attribute-based methods lack in applying controlled semantic edits. We compare our method against style flow on the task of style editing. Here we show results for de-aging. Though our model is never trained explicitly for the de-aging task, its results are comparable to style flow, a model which is explicitly trained on the task. In summary, we introduce a new editing framework called S2-Flow which enables control edits in semantic and style space. We achieve this by disentangling a pre-trained GAN's latent space. Here are the main contributions of our work. Normalizing flows can be used for the task of disentangling the latent space. We introduce transformation-based consistencies that help in disentangling the latent space. Our model is one of the first to offer control style and semantic edits. Finally, our model's edited latent vectors are amenable for further edits and can be used by other editing methods. Thank you very much for your attention. We hope you enjoyed our talk. For further information, please read our paper or dive into the code.